Very good morning, students. Today, chemical kinetics video 2. We are discussing some previous board point of view and related questions. In that, the first question is name the factors affecting rate of the reaction. Name the factors affecting rate of the reaction. 2 marks question, student. Directly they will ask. There are 4 factors: concentration of reactants, nature of reactants, temperature and catalyst. Concentration of reactant, nature of reactants, temperature and catalyst. These 4 factors can affect the rate of the reaction, can increases the rate of the reaction, The last 2 factors, temperature and catalyst, indeed we are discussing in the further coming topics, that is effect of temperature and effect of catalyst on the rate of the reaction. Okay, student. Next question. What is the rate law or rate expression and rate constant? What is the rate law or rate expression and rate constant? Here 2 topics, students. One is the rate law, next one is rate constant. Let us consider A moles of A plus B moles of B gives rise to products. For this chemical reaction, the rate of the reaction directly proportional to concentration of reactant. Their power is raised to the may or may not stoichiometric coefficient. Here x comma y are the powers of the concentration of reactants A and B. Here x may be equal to A or y may be equal to y. Sometimes may or may not equal to the stoichiometric coefficients of reactant A and B. But the rate of the reaction always directly proportional to the product of concentration of reactants. Their power is raised to the may or may not stoichiometric coefficient. Here the concentration of the power of concentration of A is x, the power of concentration of B is y. Here x is equal to may y or may not y. Y is equal to may stoichiometric coefficient B or may not y. There is no necessary condition x is equal to y or y is equal to B. For the proportionality, there is one constant. Rate is equal to somewhat constant k into concentration of A to the power of x, concentration of B to the power of y. This is known as rate law or rate expression. The relationship between rate of the reaction, rate constant and concentration of reactants are known as rate law or rate expression. Rate is equal to somewhat constant k into concentration of A to the power of x, concentration of B to the power of y, where k is known as rate constant, velocity constant or specific reaction rate. This is known as rate expression. The rate expression can be defined as follows. That is the expression in which the rate of the reaction given in terms of molar concentration of reactant with each concentration term raised to the power which may or may not equal to the stoichiometric coefficients in a balanced chemical equation. Here, student, the rate of the reaction directly proportional to the molar concentration of reactant and each concentration term raised to the power which may or may not equal to the stoichiometric coefficient in a balanced chemical equation. This expression is known as rate expression. The expression in which the rate of the reaction given in terms of concentration of reactant with each concentration term raised to the powers which may or may not equal to the stoichiometric coefficients in the balanced chemical equation are known as rate law or rate expression, which is also known as another form is there rate equation, rate law and rate expression also. Next, student, this rate constant or velocity constant or specific reaction constant or specific reaction rate are also defined as follows. That is, the rate constant of the reaction is equal to the rate of reaction when molar concentrations of the each reactant is taken as a unity. That is, the rate constant of the reaction is equal to rate of the reaction when molar concentrations of the each reactant is taken as unity. For example, 1 to the power of x into 1 to the power of 5, nothing but 1 into 1, that is equal to 1. Therefore, the rate constant of the reaction is equal to rate of the reaction when the molar concentrations of the each reactant is unity or 1. That is known as rate constant. That is known as rate constant. In examination point of student, define rate law and rate constant, or define rate constant. These two definitions we are expecting student. Okay, copy this. Okay students, next question we are discussing. Define molecularity of the reaction. Define molecularity of the reaction. The number of reacting molecules taking part in a chemical reaction are known as molecularity. The number of reacting molecules taking part in a chemical reaction are known as molecularity. For example, ammonium nitrate upon decomposition gives nitrogen and water molecule. Here, one reacting molecule takes part in a chemical reaction. Hence, molecularity is 1. That is unimolecular reaction. Uni means one, molecular means one molecule taking part in a chemical reaction. Here, molecularity is 1, which is known as unimolecular reaction. Second example, 2Hi gives H2 plus I2. Here, two reacting molecules are present, hence it is bimolecular reaction. 2 moles of nitric oxide react with oxygen to form nitrogen dioxide. 2 nitric oxide, 1 oxygen molecule take part in a chemical reaction. Total 3 molecules are present, hence it is known as termolecular reaction. Termolecular reaction depends upon the number of molecules taking part in a chemical reaction. The molecularity may be 1 or 2 or 3. These reactions are known as unimolecular reactions, bimolecular reactions, and termolecular reactions. One interesting point, the molecularity of the most of the reactions less than 3 or 3 only. In very few reactions, the molecularity will be more than 3. More than 3. You can observe students, in any reaction the reactants may be 2 or 3. In rare cases only 4 or 5 reactants will be present. That's why we will give a conclusion. The molecularity of the reaction may be 3 or less than 3. In very few reactions only more than 3. Right student. Next one, define order of the reaction. Order of the reaction. The sum of powers of concentration of the reactants in the experimentally rate equation for the reaction are known as rate order of the reaction. The sum of powers of concentration terms of reactant. Concentration terms of reactants in the experimentally determined rate equation for the reaction are known as order of the reaction. Let us consider one chemical reaction. A moles of A plus B moles of B gives C moles of C, D moles of D. Where small a, small b, small c, small d are number of moles are stoichiometric coefficients of reactants and products. Capital A, capital B reactant, capital C, capital D are products. Therefore, the rate expression, the rate law can be determined experimentally. It is not obtained from the balanced chemical equation like molarity from the equation. It can be obtained experimentally only. The rate equation can be obtained experimentally only. Therefore, rate of the reaction is equal to somewhat constant K into concentration of A to the power of X, concentration of B to the power of Y, where X and Y can be determined experimentally. X and Y can be determined experimentally. The powers of concentration terms in the rate equation determined experimentally are known as order of the reaction. Therefore, order is equal to X plus Y. X plus Y. The sum of powers of concentration terms are known as order of the reaction. Here, student, for this reaction, the molecularity will be A plus B. Why? Because 2 are the molecules taking part in a chemical reaction. Whereas the order of the reaction cannot be determined from balanced chemical equation. Definitely, you can require the rate equation. You can require the rate equation. That's why they will tell molecularity can be determined theoretically from the balanced chemical equation, whereas order of the reaction cannot be determined theoretically. They can determine experimentally from the balanced chemical equation. Experimentally by using the rate equation. Here important point, student, the X and Y may or may not equal to stoichiometric coefficients A and B. Sometimes X and Y equal to A and B. Sometimes X and Y are not equal to A and B. There is no necessity condition equal to A as well as equal to B. Let's student try. Therefore, next one. What is order of the reaction and molecularity of the reaction for the given reaction? Now we are applying one question. How can you determine molecularity as well as the order of the reaction? Let us consider whose rate expression is given. Rate is equal to K into concentration of A into concentration of B to the power of 1 by 2. Here the chemical reaction is given 2A plus B gives C plus D. 2A plus B gives C plus D. And rate equation, rate law, rate expression they are given. Rate is equal to sum of constant K into concentration of A into concentration of B to the power of 1 by 2 to the power of 1 by 2. Therefore, order of the reaction is equal to, here power is not there means power is 1. Always something power is equal to same term. Power is not there means to the power of 1. 1 plus 1 by 2. 1 plus 1 by 2. That is equal to 3 by 2. That is known as order of the reaction. We know that from the balanced chemical equation, the order of the reaction cannot be determined. Only from the rate law is given, then only you can determine order of the reaction. Rate is equal to somewhat constant K into, that is known as rate constant, A to the power of 1, B to the power of 1 by 2, 1 plus 1 by 2. The sum of powers of concentration terms of reactants experimentally determined rate equation are known as order of the reaction. Therefore, powers is 3 by 2. Hence, the order of the reaction is also 3 by 2. Order of the reaction also 3 by 2. And the molecularity will be 3. Molecularity means which can be obtained theoretically from the balanced chemical equation. The number of reactant molecules taking part in a chemical reaction are known as molecularity of the reaction. Here, reactant molecules A is 2 and B is 1. Totally 3 reactant molecules are present. Hence the molecularity will be 3. Hence the molecularity will be 3. A reactants are 2 in number, B reactants are 1 in number, hence 2 plus 1. Hence therefore the molecularity will be 3. Like this, in PU board point of view, they will ask order of the reaction or molecularity of the reaction. Remember student, the order of the reaction experimentally determined, it is not obtained from balanced chemical equation, whereas the molecularity can be determined theoretically from the balanced chemical equation. Clear students? Copy this. Okay students, next question. Give any 4 differences between order and molecularity of the reaction. Give any 4 differences between order and molecularity of the reaction. There are 4 differences student. First one order, second one is molecularity. The sum of powers of concentration of reactants in the experimentally determined rate equation are known as order of the reaction. Order of the reaction. In the previous question already we discussed. The sum of powers of concentration term in the experimentally determined rate equation are known as order of the reaction. Molecularity means the number of reacting molecules or reacting species involved in a simple reaction are known as molecularity of the reaction. The number of reacting species involved in a simple chemical reaction are known as molecularity of the reaction. If one reactant molecule unimolecular, 2 reactant molecules bimolecular, 3 reactant molecules termomolecular reaction. For this experimental information is not required. Second point, it is determined experimentally. Why? Because for a given chemical reaction, the rate equation can be determined experimentally. From the rate equation, the order of the reaction can be determined experimentally. Hence, it is clear that the order of the reaction can be determined experimentally. The order of the reaction can be determined experimentally. Next one. It is theoretically calculated. It is theoretically calculated. The molecularity of the reaction theoretically calculated. Theoretically calculated. Why? Because 2 reactant molecules, molecularity is 2. 3 reactant molecules, molecularity is 3. For this, experimental evidence is not required. Therefore, it is theoretically calculated. Next one. The order of the reaction may be 0, may be positive, may be negative, and a fractional also. 0 order is possible, first order is possible, -2, negative order is possible, 1 by 2 order is also possible. Why? Because it is sum of powers of concentration terms in the experimentally determined rate equation. That's why the sum of powers may be 0, may be positive, may be negative, may be fractional also. Next one, in case of molecular. The molecularity is always a simple whole number. It may not negative, it may not fractional, it may not 0. Why? Because the molecularity is always a simple whole number. That is, 2 is the molecularity, 3 is the molecularity, 1 is the molecularity, but not 0 molecularity. 0 molecularity means 0 reactant molecules. That reaction is not possible. Minus 3 reactant molecules, the reaction is not possible. 1 by 2 reacting molecule is not possible. The number of reacting molecules present in a chemical reaction is always simple whole number, maybe 1, maybe 2, or maybe 3, but not fractional, but not negative, but not 0. Okay, student. Next one. It is determined, it is obtained from the rate equation. The order of the reaction is always obtained from the experimentally determined rate equation. Even chemical reaction is given, rate equation they are not given. It is not possible and highly impossible to determine order of the reaction. Hence, it is obtained only from rate equation for a particular chemical reaction. Very important point. Without rate equation or rate law or rate expression, the order of the reaction cannot be determined. Whereas it is obtained from the mechanism of the reaction. The molecularity of the reaction can be obtained by using the mechanism of the reaction. If 3 reactant molecules, molecularity is 3. 2 reactant molecules, molecularity will be 3 or 4. Depends upon number of reactant molecules in a chemical reaction, you can determine the molecularity. These are the differences between order and molecularity. Okay, students, copy this. Okay, students, next question. Which step of the chemical reaction decides the order of the reaction? Which step of the chemical reaction decides the order of the reaction? This question is given in written model papers. The answer is slowest step. The answer will be slowest step. Why slowest step? What is slowest step? We are discussing small example, student. Let us consider a chemical reaction. The reactant A can be converted into product B. The reactant A can be converted into product B. This is known as simple reaction, elementary reaction, or single step reaction. The reaction which can take place in only one step are known as single step reaction or elementary reaction or simple reactions. In one step, the reactant A can be converted into product B. But complex reactions are present. In the case of complex reactions, the reactions in which the reactant A can be converted into product B by using some multiple steps. These reactions are known as complex reaction. In the case of complex reaction, the reactant A does not convert it into product directly. Indirect steps are required. That is A to B, B to C, and C to D, and C to D. For example, here 3 indirect steps are present. 3 intermediate steps are present. A to B is first step, B to C is second step, and C to D will be third step. By combining these 3 steps, the reactant A can be converted into product D. Therefore, this reaction is known as complex reaction. The chemical reactions in which the reactant can be converted into product D by using multiple steps are known as complex reactions. For example, in these multiple steps, in these indirect steps, one step is known as slowest step. That is, slowly the reactant can be converted into product. That is known as slowest step. The step in which the reactant can be converted into product very slowly are known as slowest step. The slowest step can be used to determine the rate. Hence, the slowest step is known as the rate determining step. The rate determined step, rate equation can be determined. From the rate determined step, rate equation can be determined. That word gives the meaning. Rate determined step. The step that can be used to determine the rate of the reaction are known as rate determining step, which is the slowest step. Which is the slowest step. Next one. Therefore, from the rate equation, order of the reaction can be determined. From the rate equation, order of the reaction can be determined. Now, sequence student, from slowest step is the rate determining step. From a rate determining step, rate equation can be determined. From rate equation, the order of the reaction can be determined. You know the student, in the differences we are discussing, the order of the reaction can be determined experimentally from the rate equation. But rate equation is obtained from slowest step. Indirectly, which step of chemical reaction decides the order of the reaction means slowest step of the chemical reaction determines the order of the reaction. Clear student? In the case of slowest step, that is the rate determining step, from this step we can determine rate equation or rate law or rate expression. From this, the order of the reaction can be determined. Sometimes students in examination they will ask, what is rate determining step? Slowest step is known as rate determining step. The step that can be used to determine order of the reaction in the complex reactions are known as rate determining step. Clear student? Here, what is rate determining step means the step that can be used to determine order of the reaction in a complex reaction are known as rate determining step. Order of the reaction in the complex reaction always obtained from the slowest step only. Clear student? Right. This answer you can remember. It is given in the written papers. Next question student. Define zero order reaction and give example. Define zero order reaction and give example. Definition student. The chemical reaction in which the rate of the reaction directly proportional to the zeroth power of concentration of reactant are known as zero order reaction. The reactions in which the rate of the reaction directly proportional to the zeroth power of concentration of reactant are known as zero order reaction. Let us consider one chemical reaction. 2A gives rise to products. Here, the rate of the reaction directly proportional to concentration of reactant, zeroth power of concentration of reactant. That is known as zero order reaction. Let us consider a chemical reaction. 2A gives rise to product. According to definition, the chemical reactions in which the rate of the reaction directly proportional to the zeroth power of concentration of reactant, that is known as zero order reaction. For the proportionality by using constant, rate is equal to rate constant into some a to the power of 0. Something power 0 is equal to 1. Hence, rate of reaction is equal to rate constant. Okay, student. In exams they will ask, for which order reaction, the rate of reaction is equal to rate constant. For zero order reaction, the rate of reaction is equal to rate constant. At the same time, in the case of zero order reaction, the rate of reaction is independent of concentration of reactant. In this rate equation, is there any concentration term, student? There is no concentration term. Hence, if you increase the concentration of reactant or decrease the concentration of reactant, there is no change in the rate of the reaction. Why? Because the rate of the reaction is independent of concentration of reactant. Due to this reason, the zero order reaction can be defined in another way. That is, the chemical reactions in which the rate of the reaction independent of concentration of reactant are known as zero order reaction. The reactions in which the rate of the reaction independent of does not depends on initial concentration of reactant are known as zero order reaction. In exam student, these two types are what we are expecting. For which order reaction the rate of reaction independent of initial concentration of reactions, or for which order reaction the rate of reaction is equal to the rate constant, that is also zero order reaction. In examination student, this will be a comfortable definition for you. The chemical reaction in which the rate of the reaction directly proportional to the zeroth power of concentration of reactant are known as zero order reaction. Clear student? Next one. Three examples are there. These are the memory-based examples by our student. Decomposition of ammonia in the presence of platinum element at 1130 Kelvin to form nitrogen and hydrogen. Here, the rate of the reaction directly proportional to the concentration of reactant, that is ammonia, to the power of 0, because it is zero order reaction. Decomposition of ammonia in the presence of platinum at 1130 Kelvin is a good example of zero order reaction. Similarly, photochemical reaction on the water surface between hydrogen and chlorine to form HCl, it is also zero order reaction. According to concept, the rate of the reaction directly proportional to zeroth power of concentration of reactant, concentration of hydrogen to the power of 0, concentration of chlorine to the power of 0. Why? Because the rate of the reaction directly proportional to the zeroth power of concentration of the reactants. Last example, decomposition of hydrogen iodide on the gold surface. Decomposition of hydrogen iodide in the presence of gold to form hydrogen gas and iodine gas. Here also, according to concept, the rate of the reaction directly proportional to the zeroth power of concentration of reactant, which is known as zero order reaction. These three examples, remember student, define zero order reaction and examples. Which step of the reaction can be used to determine order of the reaction is always square step. Okay, students, copy this. Okay, students, next question. Define first order reaction, give examples. The reactions in which the order of the reaction is directly proportional to the first power of concentration of reactant are known as first order reaction. The reactions in which the rate of the reaction directly proportional to the first power of concentration of reactant are known as first order reaction. Let us consider 2A gives rise to products. On chemical reaction, 2A gives rise to product. According to concept, the rate of the reaction directly proportional to the first power of concentration of reactant. Here A is reactant, square bracket indicates concentration of reactant whose power is 1. That is known as the rate of the reaction directly proportional to the first power of concentration of reactant are known as first order reaction. Therefore, rate is equal to somewhat constant K into concentration of A to the power of N. Rate is equal to somewhat constant K into concentration of A to the power of 1. It is known as rate law, rate equation, or a rate expression. Clear, student? This is known as first order reaction. Whenever the concentration of reactants is always 1, that is known as first order reaction. Here three examples are there, student. We are more concentrate. First one, very famous example. In 1 mark question, they will ask so many times. That is, all radioactive disintegration, that is radioactive decays, are the good examples of the first order reaction. In 1 mark question like this, they will ask student. The radioactive disintegration are the good examples of which order reaction? Are good examples of which type of order reactions? Either zero order or first order or second order. That is first order reaction. All the radioactive disintegration reactions are the good examples of the first order reaction. Very important, student. That is radium 88-226 undergo disintegration. It can form a rate of 86-222 plus 2 helium-4, which is known as radioactive disintegration reactions or radioactive decay reaction. All are comes under first order reaction. Next one, student. Decomposition of N2O5. To form nitrogen dioxide and oxygen. Here the rate equation. If the rate of the reaction directly proportional to the first power of concentration of reactant, hence that is known as first order reaction. Therefore, order is equal to 1. Similarly, decomposition of hydrogen peroxide to form water and oxygen. Here the rate of the reaction directly proportional to the concentration of hydrogen peroxide to the power of 1. That is, the rate of this reaction directly proportional to the first power of concentration of reactant. For the proportionality, rate is equal to somewhat constant K into concentration of hydrogen peroxide to the power of 1. Here order is equal to 1. Here order is equal to 1. Why? Because the power will be 1. The power will be 1. We know that the power of concentration term in the rate equation are known as order of the reaction. Here the power is 1, that is known as first order reaction. First order reaction, student. These 3 examples you can remember. First example more concentrate. The reactions in which the rate of the reaction directly proportional to the first power of concentration of reactant are known as first order reaction. All the radioactive disintegration reactions as well as decomposition of N2O5 and decomposition of hydrogen peroxide are the good examples of the first order reactions. So student, copy this.